Hey everyone, welcome to our webinar. Today we're going to be talking about how you can design and control and optimize for the modern EV battery cell and what it takes to design cells that are both long range and fast charging. The webinar is going to be hosted by myself, Thomas, and Damika here, who's joining me. So quick introductions. I'm Thomas. I'm Breathe's product manager for our embedded products, including Breathe Charge. My background is in battery validation and cell design, and I've been at Breathe for about 3 years now. It's been a great journey. So yeah, I'll hand over to Damika for a quick intro.
Thank you, Thomas. Good morning and good afternoon, everyone, from wherever you might be joining. Really excited to be co-hosting and presenting today together with Thomas on battery design and with high energy density in mind and getting more fast charge performance out of it. Yes, as Thomas said, my name is Damika. I'm head of battery modeling here at Breathe, and I've been here about a year and a half. And it's been a great period at Breathe, and excited to present our products and our software toolchain today.
Cool. So Damika and I will walk through our content today for about 45 minutes, and then we'll leave some time at the end for questions. You might see there's a Q&A function. Feel free to drop in your questions there, and we'll get to them at the end as they come to you in the moment. Great. So long range meets fast charging. We're going to have 4 sections to this. We're going to start by talking about what does the modern EV buyer actually want? What does the market say there drives buying decisions on EVs? Next, we'll talk about what it takes to design high energy density battery cells. Then look at the compromises that arise once energy density starts really getting to the upper boundaries of what's possible today. And then how adaptive charging can enable the complete package of long range and fast charging. So there was this great report that McKinsey actually put out earlier this year, and there's a lot more data to it, but this is some of the data that we thought was quite insightful. And it had consumers in Europe, US, and China rank what's in the top 5 and bottom 5 criteria for them when it comes to buying EVs. And what was found, probably to no surprise, is the top 3 metrics here: battery driving range, number 1; purchase price, very close in most markets as well. China, less so, interestingly, probably because the purchase price is so economically friendly at the moment in that market. And then we also see battery recharging speed, fast charging capability, essentially. And there were some really interesting quotes in this survey, in this report that was put together by McKinsey. And it was found that the minimum acceptable range for an EV today is about 500 kilometers. And most drivers say that 30 minutes fast charging is sufficient. That's what's required. But a third of the new buyers or potential buyers of EVs who don't yet own one really are looking at 20 minutes or less as what's driving their buying decision there and what would push them forward. So when we contrast that with what's available on the market today, this is some data that Breathe has put together based on publicly available information from the leading EV brands, both in Europe and some in China too, and North America. And you can see on the y-axis here, we have the range added in 10 minutes, which is really the fast charge metric that is starting to dominate how press releases go and how EV manufacturers really start talking about what fast charging is, because this is really about the lived experience of the EV, right? If I'm on my highway trip and I want to plug in my EV, it's how much farther does that charge get me, less so about how long does it take. Also, we like this metric at Breathe because it's difficult to cheat this one. This is based on WLTP range, which is something that if you lie about, would not to say people are lying about these metrics, but there's so many variables to the conditions of 10 to 80 charging. What was the temperature? What how big your pack, and all these things that really make that number harder to do like for like comparison. And we see here when we're looking at on the MSRPs, the vehicle, essentially how much the vehicles are sold for. And what's interesting is we do see some trends. There kind of is this linear slope that as the vehicles cost more, they start having more performance available to them. But then we start to see some OEMs and some manufacturers that are really breaking through this, particularly BMW and their Neue Klasse, and interestingly too, the XPeng vehicles that really have this insanely fast charging capability. And if we change this axis, so that the x-axis here now is WLTP range, and the y-axis is the range added in 10 minutes, we start to see a really interesting spread. And so you see where this green arrow is, it's starting to really visualize how there's quite a big spread in the appetite for risk potentially, or the capability potentially of these OEMs to actually drive fast charging performance. So, if we take 500 kilometers, that number that McKinsey said EV buyers think is what's required, we can see that some of those are only adding 100 kilometers of range in 10 minutes, while some 250, and even that fun line at the very, very top, which represents the XPeng vehicles, 450 kilometers. And this starts to ask questions: how for the similar energy densities in the vehicle or similar energy content in the vehicle, why are some OEMs capable to go so much further ahead, and why are some being a bit more conservative, and what could be the reasons there? So to answer why that might be the case, I'm going to hand over to Damarka, who's going to give us a bit of a demo in terms of how we can design high energy density cells.
Thank you, Thomas. So what I'd like to do from here is to introduce to one of our simulation products called Breathe Design. And Breathe Design is a simulation product that helps a user to evaluate how the impact of design criteria influence the performance of a battery, right? So if you're interested, you could also try this out. We have a free demo through our website. You could register and download, and we'll also share these links after the webinar as well. But effectively, it's a web Python API tool that we've developed that allows the users to start designing a given battery. And we've done this through certain notebooks. So when you start using it, you'll see a set of notebooks that demonstrate how you could, for example, investigate the influence of certain design parameters on the performance, do chemistry swaps, run dynamic simulations, and also then download various parameters that integrates with our second simulation product called Breathe Model, which is in the MATLAB Simulink environment to do more system level simulations. But in this webinar, we're interested in understanding kind of range, how we can increase range and effectively get more energy or capacity out. So I'll only be using a subset of these notebooks, and instead of going through all of them. But as always, they're getting started. And if you want to get more energy out, we first have to understand what cells do we have to work with. So in this demonstration, there are 2 cells that we have in our library. And in the case when you're working with us, you'll see your very own custom cells being parameterized and being available as part of the API. So it's more meaningful so that you can start working with cells that matter to you most. But in this case, we have 2 cells. It's the Moly P45B. This is what's freely available on the demo as well. And we've also got a Tesla cell that we've parameterized based on publications and literature open values. Whereas the Moly cell, we've done a full thorough teardown and parameterized it. And we'll be using that as an example case study to see how we could get more energy out and what will happen if we start making redesigns to it. So what are we typically interested in knowing what a battery performance is? I would say there are 2 key kind of KPIs. We call them static KPIs and dynamic KPIs. So in the case of the static KPIs, through the API, we can pick the cell we want. In this case, it's the Moly cell, and look at what are the key KPIs that the cell can deliver. For example, the capacity, nominal voltage, energy. These are the key ones that you often see typically from a spec sheet. There are also quantities you may not typically see, like what's the minimum anode voltage or the heat capacity. But these are typically not presented, but these are nonetheless static KPIs that are also of interest when it comes to dynamic simulations. But what's important is that if you want to get more range, we want to effectively add more capacity or energy density. But these are all derived quantities that are based on certain design parameters that are of importance to understand and evaluate how will the redesigns enable me to get more capacity out. And if you look at what are the underpinning design variables that contribute to this, well, there are quite a few that lead to each of these static KPIs: capacity, energy density, volume, weight, etc., for example. If you look at the design variables that one can change as part of this simulation tool, you could look at the recipes of the electrodes, the NP ratio, the voltage limit, the porosities, the thicknesses, the areal loadings, the format, the electrolyte buffers, and also a certain level of degradation. In this case, they're all switched off to 0. So the question is, how could I now start modifying or redesigning this to get more capacity or energy out to get a certain extent, to extend the range of my end use application? This is not a very trivial mapping. So we've kind of included a sensitivity of this design KPIs versus the design variables. And this is to guide the user to understand, okay, what could I change and in which direction in order to get more energy out. So in this case, the sensitivity map shows on the horizontal axis, it shows these KPIs, the static KPIs of interest, and then on the vertical, we see the design variables. So for this use case of interest for us, we want to get more range out. So I would like to increase the capacity of the cell, and the positive the value is that a positive value indicates that if I start increasing it, we'll be able to get more capacity out. So for example, in this case, I could start increasing the aerial loading of the cathode to get more capacity out, and a bit more trivially as well, I could increase the voltage limits, Vmax, but also I could reduce the NP ratio, for example, to get more capacity out. So the negative in this case indicates by decreasing it will have an increasing effect towards the corresponding KPI. And similarly, we can look at the other KPIs as well, and there's a counterbalance. So like if I start adding certain more material, the way it's going to get influenced, and as a result, there's going to be a balance in the energy density. So it's as I mentioned, not very straightforward way of understanding which variables to look at, and this sensitivity helps us to guide that in this direction. So in this case, we're going to take two examples. I've said, okay, what will happen if I decrease the NP ratio and increase the cathode aerial loading for the moly cell and see how much more energy I could get out. And that's this second notebook where I say, let's start redesigning the cell that we have. So I'll start with the moly cell again. I look at the base design parameters that we have, and we initiate two design options in order to get more energy or capacity out. I'm going to reduce the NP ratio by 5% because the sensitivity indicated by if you start decreasing NP ratio, you can get more capacity. Or similarly, I'm going to increase the cathode aerial loading by 5% to see what the effect of that's going to be on the overall KPIs. So we then prompt the get equilibrium KPIs, but now we pass in the designs that we've generated and get the new static KPIs based on these designs. So we could see stacked against each other where we started the baseline of 4.5 amp hours, and with the 5% decrease in NP ratio, we get an increase about 4.6 amp hours. The capacity goes to 4.6. Similarly, the energy density increases. And by increasing the aerial cathode loading by 5%, we get a slightly more increase in capacity. Right? In fact, we get about, if you look at the corresponding deltas, we get about 4.5% increase in capacity from the cathode loading compared to about 3.7% increase by decreased NP ratio. Right? So there's a choice to be made saying, okay, which way would we want to go and how would we interact with our cell suppliers and manufacturers to indicate if we can influence the corresponding manufacturing step to get an improved energy density cell. But that's just the static KPIs. But what does it mean in terms of the dynamic responses? So we also want to know, what do these changes mean for my voltage responses, thermal responses, and ideally also the anode potentials? Right? So as part of grid design, we then typically would move to look at the implication of the dynamic simulations based on these designs that you made. So in this third notebook, we kind of start again with a cell of interest, in this case, the moly cell. We include the designs of interest, the redesigns, so the decrease in NP ratio, and the increase in cathode loading. And now we are going to, instead of getting the static KPIs, we are going to simulate a 3C charge with the baseline cell, the designs that we've included, starting at 0% SOC at ambient temperature. And we're going to link it with a certain cell cycler. In this case, the cell cycler is a constant current charge. It's going to charge at 3C. So we're defining this based on the capacity of the cell up to 4.2. And by including the cycler together with the cell of interest and the designs, we can run the simulation and evaluate the overall responses for these new redesigns that we've generated. So this is the voltage curve that we're getting for the baseline, the lower NP and the higher cathode. Not much of a variation in this case with a 5% decrease and a 5% increase. But if you then start looking at some of the more internal variables and, for example, anode potential and temperature, we start to notice a bit more of a difference. So the resistances will change and increase slightly, as part of the designs, and this will get reflected in the thermal responses. So we started with the baseline, so the temperature on the vertical versus the time for the 3C charge. You see, okay, I started with my baseline cell. By decreasing the NP ratio by 5%, I get a slightly increase in temperature, and with the 5% increase in the area loading, I get a slightly about a 1 degree increase in the corresponding temperature behavior as well. And we could then also probe what's the implication on the charging behavior by looking at the anode potentials. And over here, this is where typically you would want this to be above 0 to prevent plating. But in principle, you might have a much higher threshold because of cell-to-cell variations, and Thomas will talk more about this as well. So you could see, you could use this then to study what's the subsequent impact of these designs on the safety and potential plating aspects as well. So this is one way of increasing the energy density, but there's a much more another way that you could also get more energy out as well, and that's by effectively making the cell much larger, right? Effectively moving towards a 4680 sort of format, right? So for this approach, what we have included is that you could not only do designs, but you could also start making changes to the cell format as well. So in this case, if I start with the moly cell again and look at the corresponding format it has, the starting format, which is simply a cylindrical cell with a certain material casing, housing thickness, diameter, height, and inner diameter, we're going to simply scale this to a 4680. And it's a very simple scaling at the moment. We're going to sort of make the diameter 46, scale the height to 80, and everything else, all the other parameters are going to be the same as and remain as constraints. So the electrode recipe, the separator thicknesses, these are all going to remain the same. It's just going to get compacted and get fitted into a 4680 volume size dimension. And we want to evaluate, okay, what will this result, what sort of a cell will this result in, right? So you can set this corresponding scaling for this case, define the format, and now we can again generate the equilibrium KPIs. But now on this occasion, rather than passing any designs, we pass the corresponding format, the larger format. And we could do a side-by-side comparison of, here's where we started with a baseline cell of 4.5 amp hours in the case of the 21700. And by simply scaling the diameter and the height to a 4680, get quite a considerable increase, around about 6 times higher in terms of capacity and energy as well. So that's a considerable increase in the energy and therefore range. But what does it mean in terms of the dynamic simulations is also of interest as well. Right. As I mentioned, the recipes are identical, so there's no change in the nominal voltages or the minimum anode voltage. It's just we are kind of getting more active material into this larger format cell. Similarly, we can look at what the relative changes are. So in this case, the capacity increased by about 6.3 times the the baseline case. And similarly, gravimetric energy density increased by about 1.2 by simply changing the scales if we make a 4680, keeping everything else the same. We can then also do a dynamic simulation to understand what does it mean in terms of the voltage responses and the thermal behaviors. So as before, we define a cycler. We use the cell of interest, link it to the cycler. In this case, we can do again a 3C charge up to 4.2. Start at 10%, for example, initial temperature of 25 degrees. But now we're going to pass this larger format into the simulation run. We call the simulation, run the simulation, and look at the corresponding responses. So the green curve is what we started, the baseline, and the gray is, in this case, the 4680. It is slightly lower for reasons being there's more heat being generated as part of it, and the resistances are decreased in this case. So we're doing a 3C charge in both occasions. And when we look at the corresponding temperature response, there's more heat generated on this occasion. And as a result, the cell temperature increases, and which also supports, facilitates a bit reduction in the overall internal resistance as well. And this is looking at the total heat flux that's been generated in watts in case of the 21700 and the simple scaling of 4680. And you could also then look at what does it mean in terms of anode potential as well for these two design variations. However, like I mentioned, this is a very somewhat of a simplistic scaling mechanism. There are a lot more design choice that goes into the formats. Right? So, for example, if you look at an actual Tesla 4680, it's worth looking at the comparison of what sort of thicknesses, what sort of porosities was used, and what does that mean in compared to a simple scaling that we've done. And that's what this comparison that we're doing here is we made use of open literature publication that we know of a Tesla 4680. We included those numbers into Breathe Design. And the key differences are, of course, the Molicel has some silicon as well on the anode in its anode formulations, whereas Tesla 4680 is pure graphite and NMC chemistry based. From the cathode side, it's a bit more similar. And the silicon helps to get more energy out as you saw for the 4680. So just simply scaling the Molicel to 4680, we got considerable energy, but it'll be interesting to see what happens if the chemistry recipes changes to that of pure graphite as well. And we'll see that in a bit. And interestingly, the electrodes are much more thicker in this case. For example, it's 75 microns compared to 37 in the moly, or 125 microns in anode compared to 48. And then we use this to evaluate what the static equilibrium KPIs will be across our baseline Molicel, the simple scaling, and a more realistic design of a Tesla 4680 with all the clearances and the anode overhangs included in it. And what you notice is that we do get about 6 times higher, but it's not as much as the direct scaling of the Molicel. As I mentioned, there's silicon in there as well. And by moving to graphite, you're going to get less of energy density coming through, capacity coming through, apologies. And also the anode overhangs and some of the clearances are different between the Tesla 4680 and the direct scaling as well, which also will influence the amount of active material that we can pack within the 4680 can. Right. But the numbers aren't too far off. This this direct scaling versus what we see, and we see the amount of energy, capacity, the weight, and the volumes the same in this case that we can expect. Right. This is this is kind of the typical process we have followed at Breathe to understand what the design choices mean and what are the corresponding effects they have, impacts they have on the static KPIs and dynamic KPIs. However, we also then want to do simulations at a more system level, and that's where we then move to Breathe Model. And to enable that, we can download the parameters that we generate as part of the studies. You can bring them together. So the last notebook I would like to show is we start with the cell of interest, the Molicel. We say of the design formulation that we looked into, let's go with the reduction in the NP ratio, for example. Let's bring in the 4680 scaling into it and generate the corresponding parameter sets for that redesigned cell. What this does is it generates a JSON file with all the parameters in there and the corresponding meta information for that redesigned cell. So, for example, in this case, it's saying here's your Molicel redesigned to a certain to a 4680 format, and here's the new capacity and the area and the mass, etc., which we then can be used within the Breathe model environment, which is a MATLAB-based model. It's a MATLAB Simscape, which is an acausal modeling method, and it makes it easier to do pack simulations. You can easily connect cells in series and parallel through this mechanism. So what you're seeing right now is an example of Breathe model, whereby it's connected to constant current discharge, and these parameters that we generate can then be inputted as the parameter file number. So you could have various studies of designs, bring them into your pack simulation work, and run it in the MATLAB environment, and look at more advanced thermal boundary conditions and how does it impact the corresponding fast charging control algorithms at that stage. So that's the workflow I want to go through. At this point, I would like to also draw your attention to, you could also try Breathe Model as well as part of the demo through our website. And we've also got quite extensive documentation across all our products, which will help if you're using the demos, how to do various designs and also link it to Breathe Model as well. So with that, I'm going to hand it back to Thomas, who will now continue the discussions on the implication of these high energy cells on fast charging.
Thanks, Demika. Do you want to quickly talk about how this would work in practice for someone if they wanted to get their hands on?
Oh, yes, excellent, exactly. So as I mentioned, these the cells that you just saw are it's a moly cell, it's a commercial off-the-shelf cell. But for this to be more meaningful, the cell should be something of interest to you. And the key thing is the parameterization that needs to be done such that the cells will then be available as part of the API for you to then do these investigations and simulations. And for that process, the way we set up at Breathe is we start with 10 cells that you can send to our labs. We do the teardown, the parameterization, the validation, the robustness checks. So all the parameters that you saw as part of the demo were done here at Breathe for the moly cell, the internal parameters and the corresponding dynamic parameters as well. And once that is done, the cell is then ready to be used as part of Breathe Design and Breathe Model at your end for you to then look at the corresponding sensitivities, dynamic simulations, and the static KPIs.
Great, thank you. So Demika already alluded to a few of the trade-offs that start to show up in his dynamic simulations he presented when you start moving to higher energy density or even different form factors in cells. So we're going to dive a bit into that a bit deeper and then look at what we can do about that to accommodate for that, so that the end result is you keep that high energy density and you manage those compromises you need to engineer away. So we use some movie magic or TV magic here to do these simulations in the background and do a bit of a design study. And as Demika alluded to as well, we did this by connecting the electrode level designs and those recipes that Demika looked at, simulating them at cell level with some of those dynamic simulations, but then even moving to the pack and system level. So we won't show this full workflow today, but we will talk about how we are using this to look at WLTP range and the thermal trade-offs that are introduced, and therefore the fast charging you need, and what that means. If we remember that very first graph we saw, which was the range additive of the vehicle and the MSRP, how did these design decisions you're making at this electrode level connect back up to there? And so what we did is we took two chemistry systems and we put them into a 4680 format, just like Demika mentioned, and we did a design investigation between cathode loadings of 1 to 5 milliamp hour per centimeter square, and then also an MP ratio of 1 to 1.3. It's quite a large range as well, but this is, Demika showed some of the Tesla baseline values, and this is within those ranges. So we'll talk about some of the results now. So we see here, each dot on these graphs that we will show moving forward in this section represent a unique design combination of all those combinations of energy and of chemistry system, NP ratio, and cathode loading. And we see here that of all the different design metrics that drive the WLTP range, it is energy density, which is probably no surprise, but that is what is really driving the WLTP range of the vehicle design. And in particular, we see two designs, these represented by these green dots, which meet our hypothetical vehicle targets that we want to engineer further. We can see the relative impact that these different design decisions have. You can also kind of see the design space. Apologies, it was 2 to 5, not 1 to 5 on the cathode. And we can see that both the NP ratio and the cathode loading are driving the energy density respectively, and they're to different degrees. And you can see the spread here as they're all combined with different design elements. And what's interesting here already is we can see if you want to hit an energy density 700 and above, you need to 700 watt hour per liter and above, you need to accept a certain degree of cathode loading, which will introduce, as we see later on, some different design challenges. For example, as well, like these cathode loading values are quite high. If you're thinking about 5 milliamp hour per centimeter squared, you're probably talking about dry coating. And then therefore to access 800 watt hour per liter with this design, you probably are thinking about a bit more risk or a bit more cost on your production side and how you can scale that up if that's really what you need for your application. And you can see how as you move on those different technology scales at the electrode level, what that might mean for your vehicle level. So again, this ethos of connecting everything in one go. Similarly, on the NP ratio, you can see an NP ratio of 1 is maybe not the most realistic, and due to the safety concerns that might bring in. And what this is showing is how we can cast a wide net to understand, map out the space, and then in this design environment, as you would do further and further iterations, you would kind of zero in. Next time we would do this round and say, okay, let's look between 1 and 1.1 and see, what is the optimization there, what is the trade off there. But again, just to paint that wider picture, but just to caveat that in case some of you are thinking, what are we doing with an NP ratio of 1? So what's the trade-off? We saw Damoker talk about the thermals. There are a lot of thermal trade-offs that also happen as you move to these higher energy densities. That was alluded to already, just by moving from 21700 to 4680, that large cylindrical format as well. It's not so great at distributing the heat from the core to the surface. But what we also see here is that when we apply a 3C fast charge to meet what the modern EV buyer is looking for of around 20 minutes fast charging, we see that the minimum anode potential in these simulations starts to get lower and lower and lower. And this is progressive with energy density. And we even in some cases here see it's below 0. So what we did is we did a study to look at a 3D representation of this 4680 cell with side cooling, which is conventional and is required to really get the performance out of these cells. The top and bottom cooling don't really work due to where the placements of all the current collectors are. Or the tapless current collectors, you could say. And what we see here is that where this cooling is, and under this 3C load, due to the thermal resistance within this cell format, is that you need about 30 millivolts of anode potential margin in your bulk to make sure that across your entire cell design spatially, that during that 10 to 80 charge in a normal condition, you're not going to see any risk of lithium plating. So this is the compromise we now need to look at. EV buyer wants long range and fast charging, but how do we go about accessing these green dots, these cell designs that enable the vehicle performance that we would like without compromising longevity or durability or even safety? So that's what we'll talk about now, is we'll look at the different fast charging approaches we could take to deliver the complete package that the EV buyer would be looking for. So we talked a lot about let's say the hardware designs, the hardware choices you make. And at Breathe, this is really how we see this in battery design: is the hardware is setting the limits. So this is the absolute maximum that you're given a physical design can handle. And if you want to push to certain energy densities, it doesn't matter what control or estimation you put onto it. That's limited by the hardware. And so you need really great design to make sure you're playing in the right space. And we talked about the design clouds and we showed them there, and to make sure that you're landing in the area that's going to put your vehicle or put your product into its leader in its market category. But then we see software is how you navigate the margins within the limits that you place. And having the right software enables you to be able to control the margins you need to control. We just talked about more anode potential briefly previously. We'll see as we dive deep into that moving ahead. The precision at which these margins can be set, the better your software, the more accurate you can set these, and therefore the more close to certain limits you can place them. And then also importantly, how are these margins managed throughout life? For example, if there's risk of aging as the cell becomes less and less capable, how are you adapting to that? Or equally, how do you make sure that the performance of your vehicle or your product isn't suffering as the cell, as your battery ages, and you can keep delivering the maximum power and the charging time that your customers bought and expect at the start. And this is a really interesting story in EVs where we see residual value is not as good compared to combustion engines, and you need to think from a software point of view what you can do to help make that performance, that feeling of these becoming less valuable or less performant, going away. So there's two approaches we can take, or two approaches we see at Breathe that you can take to make sure that you're managing this required 30 millivolt margin that our study told us is required. In the top here, you can design a lookup table. This is quite conventional in lots of battery applications, but especially in the automotive space. And here we have an example of one where you have state of charge and temperature as the inputs, and based on that, you get a charging current. Or we can think about using Breathe Charge, which is a physics-based adaptive charging software. Just quickly, what Breathe Charge is and how it works before we start talking about how it can help in this scenario. So Breathe Charge is adaptive charging. The three main pillars is that it's real-time physics-based estimation that we embed on device. So the work we've done with Volvo and Bang & Olufsen and all the Oppo handsets that we're on, Breathe Charge sits on the chips on those devices, and in real time is performing these physics-based estimations, taking state of charge, voltage, temperature, and current using our proprietary super lightweight model to estimate the anode potential and electrode overpotentials. So we're estimating, and then with that estimation, we're actually able to control for these different margins. So in this case, we can define a set point, a threshold, and say, make sure that this is not exceeded throughout the lifetime use of the battery, and recharge will regulate the charging current to maintain that. And importantly, it's adapting to the battery as it ages. So recharge inherently adapts. It doesn't require any lookup cycles or any health checks. It's based on the information of state of charge, voltage, temperature, and current. It's able to update its estimations of the given internal states and change its regulation of current accordingly. So as a quick deep dive into it, but we'll see it come to life now and the advantages of it versus step charging when we look at the application that we've designed. So we had our 30 millivolt margin threshold, and with recharge, we can simply set the margins that we want to control for. These can be a constant, as they are in this case, or they could be functions of really anything, but commonly state of charge or temperature and things like this, or so that we can make sure we're really getting the most out of the battery without overstressing it. But for this simple example, we'll go for a constant margin threshold. And recharge is able to maintain this anode potential threshold by regulating the charging current using closed loop control of the charging current. So we see here we have state of charge and C rate, charging C rate on the plot here, and we're going from 10 to 80, and we see we have our maximum current limit here of 3C, and then as the current starts to get quite smooth, that's on a second by second basis. Recharge is estimating what the anode potential is, and then using closed loop control, as you saw, to regulate that anode potential. So this is not a predetermined profile. Every time the battery's plugged in, every time the product's plugged in, recharge is going to be running these estimations in real time to identify how this needs to be controlled. So that's one way of getting the 30 millivolt margin in place, which would enable our vehicle to meet its targets. But what about if we just made a lookup table? That was the alternative we showed. So here, what we did is we made a lookup table with 5 degrees C breakpoints and 1% SOC breakpoints, which is very kind of common of the structure of a modern automotive lookup table. And we can see in gray here on this plot the sort of digitized look of this. And we see at the beginning of life, the step charge current tracked very closely to the breathed charge current. And what that means is when we look at our anode potential plot, we see reasonable control of the anode potential using this approach. But again, the cell is at the beginning of life here. So you can say at the beginning of life, a lookup table approach for following this similar strategy can get a similar performance out of the cell. But what happens when the battery starts to age? So we have an additional 2 lines here. So bear with me as I go through all these different lines and I explain it. So we have in the dark green, we have breathed charge charging a cell that is fresh, beginning of life. In the light green, we have recharge charging a cell under an aged condition. We have the gray and orange when the cell is charged with the lookup table, and we see in the orange that same age condition, how that lookup table approach adapts to that. And we see with the recharge approach, this decrease in the current to manage the cell to not overstress it because it's adapting real time to how it's aged in this particular aging condition. However, we see the orange line very similar to the gray line. So meaning there hasn't been too much change in how the lookup table approach, where you have a state of charge and temperature as the inputs, is treating the battery cell during a fast charge moment. And the impact of that, when we look at the anode potential, is we see this really large dip in the orange. So this is, again, the lookup table that was designed around the beginning of life performance of the cell to maximize it. But we see then as the cell ages that we're into a damaging anode potential region. And this can bring a lot of risk of durability. Maybe the cell will die faster and will lose capacity, maybe reliability even, or potentially even safety concerns as you start getting to really negative anode potentials, or really, or even parts of your cell get into negative anode potentials again, as we think back to our simulation we ran where we're 3D resolving the anode potentials in the cell. It might be difficult to see here due to the very strong overlap, but breathed charge in the small on the left-hand side, that arrow, it is adapting to the change in the anode potential, but it's maintaining that margin threshold. There is no overshoot and no undershoot even. It's still that 30 millivolts that was required to maintain it is able to be held. So let's try to get the lookup tables to work to the same degree, and let's be a bit more defensive. So now what we're doing is we are taking in the light green again, the breathed charge on the age cell, and we're going to parameterize the lookup table on that. So we're saying that I know if the cell gets that aging condition with my lookup table, I should be relatively healthy. And so we're charging the black line a cell at the beginning of life using a lookup table. And we can see here it has again, using this approach of lookup table generation, getting pretty good alignment on the age cell. But what happens is there's quite a bit of underutilized cell performance here. So we look at the black and the green lines. We're talking about a beginning of life cell, and with recharge, we're able to push that cell notably faster, especially in that 40 to 60% region. And what this means is your component that's one of the most expensive in your system, the battery cell, you're underutilizing it, and there is more performance that could have given to your driver and to your your vehicle as a whole, and it could have been more attractive offering. But because you had to take this defensive position to not overstress it or not drive risk, you had to step back. And that's really exemplified in the NO potential plots as well. You can see here the large degree of NO potential that's not close to the required margin needed, but is being underutilized, and we see it again. And so that's really one of the big advantages of using real-time physics-based charge control, is especially one that adapts to the battery cell, like recharge, is that no matter what the initial state of charge is, no matter what the ambient temperature or the measured temperature on the battery cell is, or the aging state is of that battery, that you are going to maintain that margin because it's inherently designed to adapt to it. And this is really helpful when you start to think of a battery in the world within a customer's hands, or a customer who's driving around, is that there really is intractable number of ways that a battery cell can age, right? You could fast charge it and then leave it in your garage for a really long time and then put it on the truck, or you could drive it every day in the city or drive it every day on the highway, right? And all of these are going to lead to different aging conditions. So even in this hypothetical world where there's a single aging condition to be defensive against, that's only the one. So then you start to think about how many different whack-a-mole trade-offs you're going to have to make to maintain that balance of performance and not overstepping your margins. And that really, just to summarize all this, many lines again, just to summarize this, we see in that orange, if you want to get the most performance you can out of a static lookup table, you run a really large risk of overstretching the cell, or you have to make that choice of, do I want the defensive lookup table approach? And with recharge, you don't have to make that decision. You can just say, I know what my margin needs to be. I can do my studies and understand how that spread will be based on my system design, and I can account for that and be sure that I'm always going to push the cell just as much as it can go, but no further. Yeah, and I think that really hopefully brings to life this story about software navigating margins and the importance of not only precision, we assumed equivalent precision in this case, but also the methods you use and how they are reacting. And so we really see this idea when you're designing your battery, your vehicle for high energy density to deliver that long range, knowing that you're going to put a real-time physics-based controller on the vehicle really simplifies, but also pushes the performance you can get out of that design and lets you access those more performant designs without having to be too stressed about the compromise of NO potential plating and fast charge performance, knowing that you're able to manage those margins. And we think back to that. As a volumetric energy increases, that risk just gets higher and higher and higher. Yeah. So to loop it back to the very start, we showed this graph of each dot. For those who might have missed this, each dot on here represents a vehicle. This is all publicly available information, but these are the vehicles on the market today, mostly in the West. And we see the range out in 10 minutes, how much energy you're charging into your battery, and the range, i.e. the energy capacity of your vehicle. We see there's a really large spread in how this plays out in the field and what's available to customers. And this, is a big opportunity while the EV market is still maturing to stand out and to separate from the pack here. And we really see, we talked a bit about the compromises you might have to make with risk, and we can see that come to life here, where there is a difference not only in the risk that might be being taken, but also the methods available or the capabilities of different OEMs to actually deliver on this risk. And something like recharge is one way to really de-risk it while pushing your performance up in the range added metrics. And yeah, you can see that here with our work on Volvo and the ES90, where you have the green dot with the white circle on it, and how with recharge we improved the range added by 38% and really pushed it back in line and even above many competitors in its space. And you can see here again, just a reminder of how not only varied the performance is in fast charging in the EV space, but also how you have companies from China, for example, with XPeng, which their XPeng vehicles are, these G6 and G9 are available to buy in Europe, and the pressure that not only to be on the, let's say, the Western trend line of what's possible in performance, but find ways and find new design methods and new approaches to battery development to really push forward and not only keep up with the competition, but set yourself apart and really capture the EV market share. So that's quite a lot of information. I hope it was interesting and enjoyable. And if there are any questions, we will have a Q&A session here. But I will also say that our team, myself and some others, so great colleagues at Breathe, will be at AABC North America, the 8th to 11th of December. If you're also there, please feel free to stop by our booth number 211 and say hi, have a chat, talk about this in more detail, or just talk about any battery interesting battery insights you might have. We do love to talk about batteries at Breathe. So hope to see some of you there. And finally with that, we will pause for our Q&A session now. We have 15 minutes or so left scheduled. And if you aren't able to stay or if your question, if you have you more time to go into it, you can also reach out, get in contact with Damoka and I. We can set up a call after this. And again, we'd love to chat and hear what you think or how you're approaching battery development and how you think, if you see space for physics-based software and part of the workflow of going from electrode to vehicle performance.
Thank you, Thomas.
Right.
All right.
So I will check the Q&A. We do have one question here from Elena Marsh. Thank you for the question. And that is, what features are you adding to keep up with the rapid pace of in your design products? Mm-hmm. Damoka, do you want to take this one?
Sure, absolutely. Thank you. That's a great question because the workflow that we presented today is just one of many possible workflows, and it was focused predominantly on getting more capacity or energy density out. And we did this by looking at the format changes and NP ratio and cathode loading. But I think there are other challenging areas as well. And there's examples that we already include, which is like, what if I add more silicon into it? What if I bring in LFP? What's the implication of chemistry swaps on it? And as part of that, we are working in building a material database as part of the Breathe design. And it's not ideally what we want to make sure the materials are characterized in a certain standard way. So we're working with material suppliers to make sure that the experiments that we do at Breathe the measurements are therefore standardized and can be used in a way that is meaningful for subsequent dynamic simulations. There are databases out there that we can use from open literature, but they are quite varied in the way they've been performed, and this could add some uncertainties. So one area is to be able to bring in more different materials, different flavors of silicon, LFP, NMC, graphite materials into the design space. So that's one area that we are actually working on. And the other, I would say, is also the format changes. So what you saw today was somewhat of a straightforward scaling of the format. There are many more design parameters that goes into it, like what's the anode overhang, what's the clearance, what are the lateral dimensions, not just the thicknesses. And to be able to include them is important, not just for the static KPIs, but also for the thermal responses and being able to understand that. So I think that's the other that's one of the other directions we're also looking at is how do we bring in further advanced format changes together with the material databases into our workflow. If you go through the other notebooks that we have, not just the ones I showed, you'll see this chemistry swap where we add more silicon, for example, into some group 14 material in there, and also look at cell-to-cell variations. But the near term is getting this material databases and more format changes. To be able to do more format changes is going to be key. And that's what we're working towards.
I'll just add to that quickly too. I think it's a really interesting. I mean, one of the most fun parts about working in the battery space is how let's say like how varied the market or the industry is at approaching the problem of providing energy storage. And you see all the different form factors, and you see huge prismatic and large cylindrical now, and pouch is still around as well. And so there's no clear single answer to this. And I think the sort of workflows we talked about today, when you can start from that electric level and then scale it up, and then understand the margins you might need to see how much of that performance is actually going to be accessible on my vehicle. So just not only at the electric level does it look good, or the cell level, but is this something that can be cooled properly, or when I fast charging with the entire system in place, or my anode potential margins just going to be so massive because of things like thermal challenges and different material properties, or even current collector placements and things like this, that mean that you're practically really limited to actually getting the performance you're trying to get out of it. And so doing it in software to be able to, with physics, we really believe at Brief is just the right way to do some of these extrapolations with sense, essentially. Yeah, really push the boundaries and keep finding, maybe we will one day in 15 years, all batteries on an EV will look the same, maybe not, but, to really, there is potentially you can still see in the variation in how
Yeah.
vehicles perform with the new BMW platform. You see the amazing work done by them there and pushing batteries on performances and things like the 480. Be interesting to see as the industry develops, and OEMs will need the tools to move quickly and keep up and reduce the times for new platform introductions to make sure they don't fall too far behind not only competitors in the West but especially competitors from China and the East.
Yeah, I would also like to, on that point you mentioned with extrapolation, I think whenever there's simulation, it doesn't matter what sort of simulation it is it a design, is it a cell, there's always going to be uncertainties and there's always going to be thorough validation required. So I think this is crucial irrespective of the type of simulations we do, the verification validation of it, and how do we account for uncertainties. The uncertainty is quite a challenging part, like where does the uncertainty come from and how does it propagate through. This is slightly on the longer roadmap for us as well, because to be able to extrapolate meaningfully, first of all, the baseline models have to be validated, and that's something we do quite a lot here at Breathe as part of the validation report. But even for design and the plant models, for example, in MATLAB, Simulink environment, understanding what these uncertainties in the design choices mean to the subsequent responses and the KPIs is quite key, and being able to propagate that requires some further difficult computations behind the scenes, and that's something we're quite interested in. How do we bring this? First of all, how do we quantify where the answer is coming from, and how do we then inject that into our decision-making process?
Mm-hmm. Yeah, that's it. We didn't touch too much on the precision point today, but that is very much both for the hardware and the software design of things. That's such an important point. It's not only what levers do you have, but how precise are those levers, because that really will drive how much value you can get out of them. And also, again, like when you start doing those extrapolations, how accurate you can be there, and really make sure you land on something that's really innovative. All right. Thank you all for joining. It was really fun to present this work to you all. And again, looking forward to speaking to some of you in the future, both either at AABC or reaching out to us directly. There'll be a follow-up email with this on, so you can watch this back on demand. So yeah, feel free to reach out with any questions, and hope you all have a great day. Cheers.
Thanks, Thomas.